So welcome to the next video. So this video we will solve another previous year KTU problem. This was asked in 2019 December for 8 marks. This is from module 5 of MOS. In module 5 this is from the particular area of torsion. Okay, so again as I have told in previous torsion problems, we need to study only 2 problems for torsion. So make sure that for university exam, you study these 2 formulas, you can easily score some marks. So the question is, the hollow shaft of an external diameter 70 mm and diameter ratio 0.8. Shaft, okay, the hollow shaft is of external diameter 70 mm and diameter ratio 0.8. It transmits a power of 2 HP at 25 RPM. If the maximum torque exceeds the average torque by 25%, draw the shear stress distribution across the section of the shaft indicating the values. Okay, so this question is also a straightforward question. Only thing is you should know the shear stress distribution to completely answer this. Okay, now one thing that you have to notice here is the data given is as follows. We have a shaft, hollow circular shaft. The external diameter capital D is 70 mm. Okay, and diameter ratio is 0.8. So diameter ratio means it has to be it's 0.8. So it has to be small d by capital D. It is 0.8. Okay, because this value will be definitely less than this value. What is these two? Basically, so assume that this is circle. So this is the hollow shaft. This is external diameter. This is internal diameter. Okay. Now power transmitted is 2 HP. Now horsepower, HP is horsepower, 746. So this is 2 into 746 watts. Okay, 746 watt is 1 horsepower. So that's the power transmitted. RPM is given as 25 RPM. If the maximum torque exceeds the average torque by, so basically T max equal to 1.25 by T mean. Okay, average torque by 25%. So basically maximum torque is 25% more than the average torque. Draw the shear stress distribution across the section of the shaft indicating its value. So they are asking us to find what is the shear stress distribution across the section. Okay, now power is given. So power is given by 2 pi nt upon 60. Okay, so this T is nothing but mean. Okay, average value. Now we just substitute this the values. We know P, we know N. We will get the value of T. Okay. So one thing that you have to notice here is this I have told in many torsion videos. This power will be in watts, and this torsion will be in Newton meter. Okay. N is rotations per minute. So minute is that inside the unit. Okay. So I'm not writing that. So this so basically T m equal to 60 times power divided by 2 pi m. So this is nothing but 60 times the power is 2 into 746 watts divided by 2 pi n is nothing but 25. So this comes out to be so we'll just calculate this very fast. 60 times 2 times 746 divided by 2 times 5 times 25. So this is 569.9. So we can write 570 Newton meter. This is the mean torque. The maximum torque will be 1.25 times 570 mean torque. So that is, so this gives me do 1.25 712.3. It is 712.3 Newton meter is the maximum torque. Okay, so this is we have found the first part of the problem, as in this is the first part. Now we will solve the second part. So I'll draw a line here, draw a proper line here. So the second formula that you have to remember in torsion is the torsion equation, that is T by J equal to tau max upon R equal to G theta upon 10. So this is the third part. We will not be using this formula, but remember, always remember, in this equation, the value of T should be in Newton millimeter. J will be in millimeter raised to 4. Value of shear and G will be MPa. R will be millimeter. Theta will be radians. And L will be millimeter. Okay, so always remember this. Now, we know the value of T. Substitute T max here. We will get the maximum shear stress. Okay, so we can find the maximum shear stress directly here. T max equal to T R upon J. Now, for a circular section, J equal to, hollow circular section, J equal to pi by 32 into d to the power 4 minus d to the power 4. So if I can substitute all these values here, T is nothing but 712.3, 712.3. R is nothing but, R is d by 2, capital D by 2. So basically it is D is, capital D is 70. So it is 70 by 2, 70 by 2. J is pi by 32 into, so what I'll do, write the value of, so this pi 32 will go up, okay, pi by 32 into d raised to 4. So capital D is 70, 70 raised to 4 minus small d is, okay, that also we'll calculate here. Small d is 0.8 into 70. Okay, so that is 56 mm. 56 mm. Okay, so that is 56 raised to 4. Okay, so J is done. Now R is there, R is d by 2. So R is d by 2, so D is nothing but 70 by 2. Okay, so I hope this is clear. So pi by 32, 32 has gone up. Pi by 32, 70 raised to 4 minus 56 raised to 4. I hope this is clear. I hope this is not confusing. Okay. Now we will just calculate this. We will see what is the value of maximum shear stress that is coming out to be. So just clear the calculator. So it is 712.3 times 32 times 70 divided by pi times 70 raised to 4. 70 raised to 4 minus 56 raised to 4 times 2. So this gives maximum shear stresses okay, this is a small mistake here. Okay, now we will use this equation to finalize the answer. So tau max is that we have to find maximum shear stress. Okay, so what is tau max? Tau max is equal to T times R upon J. Now we know that R equal to D by 2, which is equal to so before starting this equation, what we will do, we will find the value of small d. Okay, small d is nothing but 0.8 times 70, that is 56 mm. So now we will use this equation to find the maximum shear. So tau max equal to T R upon J. Now remember that. Remember that R equal to capital D by 2, which is equal to 70 by 2, which is equal to 35 mm. J equal to pi by 32 into d raised to 4 minus d raised to 4. Okay, So 1 by j will be the inverse of this. Okay, so this we can write as t times, what is the value of r? R is nothing but 35. So value of t, always remember, don't forget that t should be in Newton millimeter here. Okay, so this will be 712.3 times 1000. This is value of t. Value of r is 35 divided by j. So j is pi into capital D raised to 4. Capital D is nothing but 70. 70 raised to 4 minus 56 raised to 4 by 32. So this 32 will go up. Okay, so this is what we have to find. So let us calculate this. So there is a calculation which I have done. So 712.3 times 1000 times 35 times 32 divided by 5 times 70 raised to 4 minus 56 raised to 4. So this gives the value as 17.91 MPa. Okay, so 17.91 MPa. Now, where is this shear stress? This shear stress will be at the edge. This shear stress will be at the edge of an element in this edge will have the shear stress of where r equal to r. Okay, so this is the maximum shear stress. Maximum shear stress will occur at the edge. Now, if you want to find shear at any other point inside this, okay, so the shear at this point will be, so we can say the shear at this point will be, shear stress will be 17.91. Also, we know that there will be no shear stress here, and shear stress will increase from this point to from center to edge. Now, since there is no material, there will be no shear stress here also. Okay, now we want to find what is the shear stress at this location. Okay, so for that shear stress, finding the shear stress, we can use the simple. This will be linearly varying. So basically, tau max upon r should be equal to tau upon small r. Okay, the shear at this location I call this tau r. So this tau r upon small r. So tau r equal to tau max upon r into r, which is equal to 17.91 divided by. So the ratio of r by r is nothing but ratio of small diameter by capital diameter. Okay, so I can use that. So r by r is nothing but d by d. So small diameter is 56 and higher diameter is 70. Okay, so this gives me my final value. So let us just calculate that very fast. So 17.91 times 56 divided by 70 gives me 14.33 MPa. 14.33. So at this point, the shear stress is 14.33, and it will be varying like this. Okay, so shear stress variation is nothing but it will look like this. At this edge, it will be 14.33. And this edge it will be 14.33. And this edge it will be 17.9. Okay, so any point on the outer diameter, it will have value of 17.91. Any point in the inner diameter, it will have values of 14.33. That will be the distribution of shear stress. Okay, so on a section, if you want to draw, that also we can draw. This is the section. So here we have maximum value, here we have the minimum value, then we have no value here. So just erase this. Then we have some value here. So this will be a linear equation. Okay, so this is the So here there will be shear stress, and in between there will be no shear stress. No shear stress. So this is a shear stress variation. Shear stress variation. So I hope this is clear. This is how the shear stress varies. So from this point, all the points in the outer circumference will have shear stress of 70.91. All the points in the inner diameter points in this inner circumference will have shear of 14.33. In between, there will be linear variation. Okay. So I hope this is clear. So this will end this problem. It's for 8 marks. We will solve another problem in the next video. Thank you.